This is absolutely ridiculous. Okay, so I clicked on OBS, and apparently the Linux version of this is just so terrible that it just immediately quit. So I have no idea what's going on. I'm not touching it again. Okay, so, right, if we end up with, like, (3.9 to 4.1), right? This is one standard deviation. We got 68%, 68.25% of the data is going to be within that. So if we wanted, again, around 3.7, no, I'm sorry, we wanted a 95% confidence interval. So if we went like 3.8 to 4.2, that's going to get us our 95.45%. And so we can play around with this a little bit and say, like, all right, if we want negative infinity to 4 is going to be a half. 3.2, whoops, 3.8 is going to get us 2.28%. So 3.9 is way too high. So 3.82, 3.81, 3.805, 04. There we go. So 3.804 is going to be the magic number for this one. Which means that above 4, that's going to be a 4.196. It's going to get us about as accurate as we're going to get here. So in this case, we had our mean was a 4 standard deviation of 0.5. And when we did the other one was mu's 4. Standard deviation is 0.1. We needed this to be 804. Do 4.196. All right, now how do we calculate it? So if we wanted this to be actually the value to get this, right? We'd want to say with a 2.5% margin of error, we'd want what is z at 0.025. Actually, what is it? So we want to do the inverse norm function. Statistics. That is not what I wanted. Okay. You know, I ask you for the statistics keyboard, and it just doesn't even do the normal, inverse normal stuff. All right, where's my other calculator? I mean, probably. All right, calculate. Statistics catalog. I. Huh. Yeah, this does not like statistics. Which is funny because it's like my 84 probably has it just fine. Yeah. Sorry. Inverse norm. We're trying to find what is the x value that's going to get us 0.025, the proper z value. Yeah, so actually this is backwards from how I wrote it before. Z of what is going to get us 0.025, right? So I have an approximate value of 1.96, but that's no fun, so... Okay, so it is close enough, but nonetheless, I just wanted to check. So z is approximate, or no. No, wait. Yeah. Ugh. Alright, cool. 1.95996 3986. Obviously more from there, but yeah. So negative 1.96 is actually close enough to just call it. So if we wanted to say again, what are the values that we had, or like how can we calculate these values or these values from all the other stuff that we had? Then we want to say like, okay, this is going to be 4 plus or minus. And then over here we said our z value is equal to x minus mu over sigma. So yeah, we want to move this stuff around. We wanted it to be 1.96, 1.95996, etc. times sigma plus mu, or mu plus or minus. We'll figure it out here. It's fine. Mu plus or minus z times sigma. Alright, so this is going to be 4 plus or minus 1.95996 3986 times our sigma was 0.1. Well, okay, 0.5 for the first one, and 4 plus or minus 1 point. Yeah, 959963 times 0.1 for this one. Times 0.5. Yeah, okay. So the actual value here. 4.97998. Right, and negative plus 4. 3.02000185. So yeah, like, not really a problem. 0.959963 times 0.1. It's going to be a 4.19599963. And negative plus 4. 3.804037. So yeah, well within the margin of error of everything we were trying to go for here. Which function, sorry? So I did inverse norm. On the TI calculators, it's just INV NORM. And so my TI-89 doesn't have it. It's probably hidden in some menu somewhere. I tried looking it up in the catalog, and it doesn't appear to be under that, at least. So that's slightly, maybe slightly frustrating. But then again, the TI-89 is not really meant to be a statistics calculator. It's meant to be like an engineering type calculator. But still, you'd think it would be, it's like Gaussian or something. But again, the TI-8384 family has always had it. I think my TI-86 back in the day also had it. And then I just looked it up on Google, so shouldn't say their name. Free advertising. All right. What else anybody want to see? So, like, we can be 95% confident that the really crappy coins are going to be between 3.02 and 4.98 centimeters. So, like, this would be, you know, minting something for a game. You know, minting poker chips or something that you, really tiny poker chips, that, you know, you don't really care about their accuracy. The second version would be something like, you know, minting coins or something where you really need to be sure of their accuracy to make sure that they're not being forged or anything like that. I mean, the government probably puts a sigma more like 0.01 on the coins, and they're made out of metal, so I mean, they're not gonna like change their shape and stuff like that much. I would be actually more suspect of the measuring tools that were used to detect the width of the coins, or the diameter of the coins, than the coins themselves. So so what would happen with them is that they would be 95% confident that their coins would fall within a smaller range, so their sigma would also be correspondingly smaller. So like I said, if it might be a sigma of 0.01 or something like that, but either way, you know, the coins would have an almost surety of being within this range. The confidence interval itself, generally speaking, you don't change it. It's going to be almost always 90 or 95% confident. But the thing that changes is your sigma. So how far apart are the actual data points getting us? How much of a deviation is there between all of the different between all the different values? So when you're trying to calculate like a sample, when you're trying to calculate a sample, boo. Alright, whatever. That's not what I wanted. I don't think this is going to do it, but... Oh yeah, it did. Okay, cool. No. That's a lot of data. This had it in a... by 6 array, so that's 72 pieces of data. But yeah, if we wanted to calculate the standard deviation of all this, right? Standard deviation is calculated by finding the sum of all... Come on. There we go. Standard deviation. It's been a while since I've done this, so you know. Alright, so standard deviation is calculated by taking the difference between every individual x sub I and subtracting it from our mu value, which is going to be the actual... so if you end up just looking at a sample, and we don't know what the population mean is, so we'd be looking at what the sample mean is going to be. But with a large enough set of data, we can be like, all right, well, the sample mean is going to approximate the population mean, so good enough. It is kind of hand wavy, but it's fine. All right, then you square the difference between them. And multiply by p of x, the probability function. Interesting. Oh, right, okay. So you're multiplying it by p of x, the probability distribution function, so that you can get a relative sample mean, or sample standard deviation. So anyway, this is going to be equal to sigma squared, which is our variation. Yeah, right. Oh yeah, we're there's a lot here. So actually, if you pop this into a sheet of some kind or another, I don't think I want to do that visibly. No offense. Just go. Just make one. Come on now. Okay, so there we go. All right, so if we want to find the... Really? Mean's not a thing? All right, okay. Average. No. I want you to find the average between A1 and F12. Okay, cool. All right, so the average of all of them is 1760. And then if we go here, this is going to be equals A1 minus, this is G3, unchange. So fill down and right. Cool. Okay, this is going to be equal to A15. Yeah. And then square it. Down right. Okay, and then this is going to be sum of all this stuff. I know you can't see it, sorry. So the sum of all this stuff is equal to 2253.58, like 5799999. So close enough. And then this one I'm going to do square root. This is G32. 47. That doesn't seem right. Hang on. I'm off by a bit. Alright, how do I do... expected value table. Okay, so what if... if we don't have a probability distribution, we just assume that it's normal. Huh. Okay, so if we do a okay. Find the mean. Find each score's deviation from the mean. We did that. Square each deviation. Find the sum. Find the variance. That's the problem. So what was the variance itself? There we go. Ah, okay. Divide by n the number of values in the population. Okay, so that's what I forgot to do. Divide the 2253 by n. So this is going to be n times sigma squared. So this thing divided by n is going to be 2253.58 divided by the sample size was 72. Where'd it go? Alright, so it's no longer that thing. So it's G32 divided by 72. That's 31.29, much better. And take the square root of that. H32 is 5.6. Yes. Much better. 5.5946. More stuff beyond that is our sigma value. Okay. For the sample, I think usually we just call it S because it's a sample standard deviation rather than a population. But again, if it's normally distributed, it doesn't much matter what you call it, it's still the same thing. So X hat, right. Okay, there we go. Yeah, so you square each one as it goes through. So the way I've got it set up on my... Here, let's drag this sheet over because it's just an OB. It's an OB sheet, it doesn't matter. Okay, so here we've got all of the individual data set. Then we said let's take the average, and you can't quite see the... you can just barely catch the bottom of it there, it's fine. But yeah, you take the average of all of that stuff, and this is what we get here. Then we said take all of those things and subtract, all of the things up top, and then subtract that one number, again, $G, $3, to make sure it just stays as G3 the entire way. And that's our difference. Then the next step was square all of them individually. And then the next step was sum all of that, divide by n, and then take the square root of that previous number. So we end up with this stuff. Sample standard deviation S. So this is going to get us 17.6 plus or minus 5.595. I don't know. Probably don't need to bother. And also this is money, so like, what are you going to do with half a cent? So this is our one standard deviation. So mu plus or minus 1 sigma. Again, this was 68% of our data. This is going to end up being a 68% confidence interval, which is terrible. But if we went with mu plus or minus 1.96 sigma, this is going to get us our 95% confidence interval. So, 5.5946. Oops. 5946154565. Okay. Times 1.9, and again, it's not going to matter. So whether we do 1.96 or 1.9, nope, 1.955, nope, 1.959963, it's probably not going to matter. All right, so 10.965, and if we add that, $1760 plus or minus 10.9652. We can leave it there because that's not going to matter at all. All right, so add this to 1760, and we get on the high side 28.565, and on the low, it's 6.635. This is a 95% confidence interval of stock prices for, what was it? Initial IPO value. So I mean, it's like wildly, yeah. Data sets. Here we go. Stock prices, initial public offering, IPO, stock prices for all 1999 stocks that at least doubled in value during their first day of trading. So that's saying that we want almost a 2 sigma confidence interval. So we were saying up here a while ago, 2 sigma itself, right? 2 sigma is about 95% of the data. It's a little bit more than that. The actual, or a closer value, right, was 1.959963, but 1.96 is so close to that nobody cares. So 1.96 is as close as we need it to be, instead of just 2 sigma. Yeah, basically. That's not to say that any stock within those prices will double on its first day of IPO trading. As awesome as that would be, the correlation does not work in reverse. But yeah, the correlation in this case is we have a 95% confidence rating that if a stock were to double within its first day of trading, it was likely offered between 663 and 2856, give or take. Yeah. So the difference there really is, do you have information a priori or a posteriori? And in this case, it is most definitely a posteriori. You're coming at this from the future looking back. This is not predictive, this is reflective. So that's one of the ways in which this kind of statistics is oftentimes mishandled. It's like people will make that opposite correlation. So we're saying here, our input is stocks that double IPO price. And then our output over here is going to be their prices. And so many people make that assumption that, again, based on their prices, they could then predict whether or not these things will double. And it's just not how the statistics works. It doesn't invert at all. Yeah. Right. Is it the right kind of company for the right time in the market for the right whatever? Yeah. Goodness. Anybody else have any other questions? Or lime, so you can keep going. That's good. So technically, right, if we were to look all the way back here, never mind. If we were to look all the way back here at the actual function for Gaussian distribution, the value that we're going to get, let's see, where do we want this to be? We were trying to look for, based on sigma, based on mu, we want to know what the z-score was going to be. Wow. We want to know what the z-score was going to be when we look at x minus mu over sigma. And here we said we're looking for 1.96. So how do we get that? That's going to be from nope, backwards. Did it again. So we're looking for what is the value of z going to be. Z is just that exponent piece. So this is going to be our... you know what? Let's use the right letters here. Oh my god. Ugh, it's so slow. So this is called the Gaussian distribution, or normal distributions. We could use n, we could use g. Generally speaking, we like to use g for Gaussian or n for normal, depends on who you ask, really. Most of the time, anybody who's like super into algebra is probably going to call it g, because Gauss. So what we're doing is we're saying that we know that the value that we want here was a 95% confidence interval. So we wanted, where is this value? Where is g going to be equal to our 0.025? So this was 1 over. And for our example, we did like a, let's do the 0.1 version. Square root of 2 pi times e to the negative 1/2 times, and here let's just use z, because I don't care. Z squared. So we're trying to solve for z. It's not particularly easy in, like, you know, an algebra sense from the standpoint of like student, but it's not particularly difficult if it's just, you know, like somebody who's been doing algebra a long time. So 0.1 times the square root of 2 pi times 0.025 is equal to e to the negative 1/2 z squared. So the 0.1 is our sigma for that one example we were doing, with the, you know, coins, trying to make them as accurate as possible. So if we make this the natural log on both sides, it's going to be the natural log of 0.0025 times the square root of 2 pi is equal to negative 1/2 z squared. Okay, we'll multiply by negative 2. Ugh. Natural log 0. Come on, man. 0.025 square root 2 pi z squared. Okay, so this is the square root of the natural log of 1 over negative 2 as an exponent, brings that up. So this is going to be 2 pi times 0.0025 parentheses squared. Ew. All right. So if we do this, this is going to be 0.0025 squared times 2 times pi equals 0.000039269908, some other stuff. We do 1 over that. We get 25,464.79. We take the natural log of this. It ends up being 10.145. It seems like it's not going to come out quite right. Take the square root, and we get 3.185. That's not 1.96. Hey. Hang on. Okay, so where did it go wrong? All right, x minus mu over sigma is just z. So we can leave that there. Okay, 0.0025 times, nope, let's try again. All right, 2 times pi. 6.28, we know that. Take the square root. And then multiply by 0.0025. Take the natural log. Multiply by -2. And we get 10.145. Yeah. And take the square root. It's the same number. 3.185. Huh. Well, we're in trouble. What happened? Alright, let's see. So, let's flip this. 0.975 times 0.1. It's be 0.0975. Alright, so we multiply this by, let's go square root of 2 pi. Multiply by 0.0975. Alright, then take the natural log. Multiply by -2. And take the square root. 1.678. That's not it. That's a lot closer. Yeah, so I took the complement of that value and tried to see if it was just that I was on the wrong side of the Gaussian distribution. Turns out no. I'm just wrong, that's all. Yeah, so I probably just did something wrong. That's fine. X minus mu over sigma is z. Okay. So we use x minus mu over sigma as z. That's z squared. We got z squared. Okay. Negative 1/2 times that in the exponent of e. Negative 1/2 in the exponent, x minus mu over sigma all squared, not the negative 1/2, just the other stuff, times 1 over sigma times the square root of 2 pi. 1 over sigma times the square root of 2 pi. Yep, well, that's frustrating. Alright, so clearly we're using the wrong one. Must be the integral of this. I don't want to do it. In fact, you can't, but... Well, I mean, it does, in the sense that, like, you need to know how far away you're talking. How steep is the curve going to be? So let's just try this, for instance, right? So 2 times pi is equal to this. Take the square root. Multiply by 0.025. That's that. Take the natural log, multiply by -2, and take the square root. It's 2.353, so that's not even, no. Right, if sigma's 1, that's going to be large. Okay, well, I'm no master of statistics. Oh well. Okay, well, it's been fun. I think we're, we can integrate it. The problem is that this is an e to the x squared function, and e to the x squared is notoriously problematic for trying to find an integral for it with normal means. You've either got to use a Taylor series approximation or use complex analysis. And yeah, I don't want to do complex analysis tonight. It's not like that hard. It's just that it's been a long time since I've done it, and I don't remember. That's crazy. Jeez. Do you know which stats class? So the stats class that I have is, or that I had to take, was regular undergraduate statistics for math majors. So yeah, that was a fun one. Yep. We used to use StatCrunch, and there's a really old system that we had, 2003-ish. I don't even remember what it's called. It's probably on my old computer still, now that I'm thinking about it. No, maybe not. Oh man, Turing's Playhouse, that was a good one. So we had a, my spouse and I did a class called Computer Power and Human Reason, which was Philosophy 410 or something like that. Didn't require anything, but basically we spent the entire semester reading science fiction texts like Asimov and Arthur C. Clarke and all these other ones, and then did some projects that like were basic programming by using Turing machines. And one of the things that we did Ooh. Oh, they did it. Good for them. There was a game that was called Manufactoria from the original Pleasing Fungus Games, and they re-released it on Steam. That's just a placeholder, unfortunately, for the moment, but man. But yeah, they released it on Steam. It's been a year or so. Yeah. That one. So the the game that we had, our programming whatever that we had was basically to accept input from a tape, and then you would decide whether the object would be dumped on the floor, i.e. trash can, or brought over to the end where it's then accepted into the whatever they had. So you would have to decide how to sort things, and then people had eventually worked it out so that like the harder levels, they were like, I'm just gonna like hard code this particular input in so that this one will work, but it won't work for like what the actual requested parameter was. So they developed something called the malevolence engine, which would find errors in your code, create a tape that would then ruin your program, and it would say, ha, cheater. But so anyway, our the actual Turing machine program that we had was called where is it? I just had it up. Yeah, it was from Tricona Software. It's called Turing's Playhouse. I mean, it hasn't existed, I don't think, in a long time. I have a random copy. I have a random copy here because it's, you know, old from. I mean, this one over here is my computer from. Basically, just been carried over data drive to data drive since college. So. But in Turing's Playhouse, you would have a Turing tape, and then you would tell it like what to put on the tape, and it just gives instructions as far as like, you know, move right, do this, move left, put something here, delete it. You know, you'd have a set of instructions that it could work off of. But Manufactoria was close in that it sort of did what a Turing machine was supposed to do. You are feeding it tapes and then telling it to follow the given instructions. So anyway, I found it interesting. I'm gonna have to go see what the new Steam version of Manufactoria is like. Maybe we'll have to play that sometime on a Friday. So we are going to check out, see who is available, what they're doing. Yeah. Alright, so Steebs is doing Resident Evil 4. Boss Lady B just started up doing Expedition Calypso for Elite. Looks like a deep space mission. Xannerly's doing Last of Us 2. Dev's doing Demonologist. Oh man. Let's... Stack Crunch. Oh, wait, no. Yeah. Stack Crunch has been around for us for a very long time. For our college. I can't remember what I actually used in college, but it wasn't StatCrunch, and it wasn't like several of the other slightly more modern softwares. I'm pretty sure it's proprietary. Let's go see Dev, I think. He's doing Demonologist. He says, this game is not even scary. Alright. Woo! Alright, so we're gonna go check out Dev. We're going to go see you all on Friday for some games. We'll see what I'm feeling in the mood to play. We have Final Fantasy VII Remake intermission that needs to be played at some point. Got the mission with Yuffie going on. We've also got, Manufactoria and/or several of the other games that I've just found out are almost identical to it. There was one on, oh yes, anybody who has Epic, there's a free game up there every week, and the one this week is actually like almost the same as somewhere between Manufactoria and Factorio. So if you like Factorio, probably like the free game this week. Anyway, so we'll be back on Friday for games. I'll see what I feel like playing. And we'll also be back on next Tuesday for more math stuff. So, have a good week. Stay mathy. Something. I'll figure out a catchphrase at some point. Anyway, this is Obi-Wan Pez for N Simplex Pachinko. Have a good night.